Hello everyone. Welcome to the live session of this course, which is Foundation of Classical Electrodynamics. So I'm Gitanjali Jaina. I'm a PMR scholar from and the team for this course. So in each live session, we'll go through the weekly content that has been discussed during this week, which is for this. I think we are now in week 6. So we'll go through the weekly content as well as I will try to solve the problems that is related to the concept that has been covered in week 6. And besides that, if time permits, I will also try to clarify some doubts that you must be having for any questions or assignment that you must be having. So for week 6, if you recall, we saw what is how we can calculate the electrostatic energy of a system. So we are still now in electrostatics, where the source charges are already at rest. So for this electrostatic situation, we are covering, covered what will be the electrostatic energy of a system. Okay, so before that, let me ask if my voice and the screen is it visible to everyone, and if my voice is audible to everyone, just let me know in the chat box. Okay. Okay, so we saw what is the electrostatic energy of a discrete charge, and for this we just take the summation of over all charges. Uh, you can see this formula. And for continuous charges, we have to take integration. If it is a surface charge, we can take sigma d as phi. Phi is the potential here, if you recall. And if it is a volume charge, you can also take half integration rho pi dV. And if not, if you know the electric field, you can also use this formula epsilon by 2 E squared dV. So using this formulation, we have seen in the lecture that we have calculated what will be the electrostatic energy of a spherical cell, which is a hollow cell, and the charges are only at the surface of the spherical cell. For this, it is q square by 8 pi epsilon a. And for a uniformly charged solid sphere, it is 3 by 5 times of q square by 4 pi epsilon a. This is all about the electrostatic energy. And so far, we have seen how we can calculate a electric field for a point charge or a some distribution of charges that we can easily calculate using the Coulomb's law. And also, we have seen how we can calculate the electrostatic field for the continuous charge distribution. It can be a line charge, it can be a volume charge, or it can be a surface charge. But so far, the problems that we have covered, it is possible to get the answer using either integration or the summation. Or if not, if the system has some symmetry, like if the charge is distributed in a symmetrical manner, then in that case we can use Gauss law to find out the electric field, and from electric field we can proceed to find out the other electrostatic parameter. Maybe it can be a potential or it can be a energy. So far it is possible to follow the Gauss law or integration or summation rule. But if you look at some more complicated problem, like if the system has some more complicated charges distribution, then for that case we can't use the simple Gauss law or the simple integration or summation rule to find out the parameters, the electrostatic parameters. So for that case, what we do, we make a approximation, which you already seen. It is a multiple expansion of a potential. So for that, whenever you have a complicated situation that you can't follow the Gauss law or you can't follow the usual method of integration or summation, for that case, you can use the multiple expansion method. It gives a approximate potential for the system. From potential, then you can proceed to find out the electric field, because for electrostatic case, electric field, you can write it as a grade negative of gradient of V. So for multiple expansion, you see, you can write the potential is a summation of either the monopole term or it can be a dipole term or it can be a quadrupole term. So or any other term which can contribute to the potential. So whenever the monopole term is zero, the dipole term dominate. Whenever dipole is also zero, the quadrupole term it dominates for the potential. So this is how you can approximate the potential for a complicated case, and from that you can find out electric field and the other parameter. So we'll see the problems related to multiple expansion as well as we'll try to solve a few problems that is related to electrostatic energy. So before that, let us uh, recall the concept that we have seen for our previous uh, lectures. So let me give you a question. So this is based on the symmetric charge distribution. So the question is easy. So there is a solid sphere of radius r, which is a charge density rho r is rho 0, 1 minus a r by r. And it is given the electric field at a distance r by 2. It is 1.25 times of electric field at r at capital R. Then what is the value for the constant A? So you are given a symmetric distribution of charges and you need to find out what will be the constant given the electric field at r by 2 equal to electric field at capital R. Sorry, 1.25 times of, let me write it properly. It is given electric field at r by 2, 1.25 times of electric field at r is capital R. So what will be A? So you can easily see these charges, the charge distribution as symmetric. So it's a symmetric distribution. So you can use the Gauss law to find out the electric field. Then from by comparing the electric field, you can easily find out what will be the constant value A. Four options are given. First option is it is 2. Second option is it is 1, and C it is half. D is 1 by 4. What will be the answer? Okay, if it is taking time, I think you can solve this problem. It's quite easy. So just let me go through the steps briefly. So for this, what you need to do, you need to take a Gaussian surface, which is symmetrical to the system we have, which is a solid sphere. And for this, you need to find out what is Q enclosed and the use the Gauss law to find out the constant value A. So Q enclosed is nothing but rho dV. It is given, it's a volume charge density. So rho dV. And dV, whenever we have theta and phi in the whole integration, so you can see rho is not a function of theta and phi. So that means you can write dV as 4 pi r square dr from 0 to r. Okay. So finding the integration is quite easy. It's in the linear form. So this is 1 4 pi and 1 by r square dr from 0 to capital R, because the charge is only enclosed inside the solid sphere of radius capital R. So if you do it, you will get RQ term here and outward flow term here. Okay. So inside you have to take a small r, right? Don't put it capital R because it will give the total charge at the surface. So if you do it, you will get this will be 4 pi rho 0 RQ minus RQ by 3 A R to power 4 by R. Okay. And it's already given. So this is Q enclosed. So E 4 pi R square will be, according to the Gauss law, it will be 4 pi 0 RQ by 3 minus A R to power 4 4R. So electric field, you will get it rho 0 by epsilon 0 uh, R by 3 minus A R square by 4R. So one condition is given that the electric field at R by 2, it is 1.25 times of electric field at R is capital R. So you just need to put it here, and if you put it, you will get the value of A is 1. So answer will be option B. Yes, it's correct. Okay. So this is just to give you a practice problem to the concept that we have seen earlier. Now we'll see the problems that is related to week 6. I will try to cover it using the concept that has been taught in the class. If you have any doubts while solving the solution, feel free to write it in the chat box or let me know if I need to unmute your audio. Okay. So the second question is it's about to find out what is the electrostatic energy of a spherical cell. So it's given a small charged spherical cell of radius 0.01 meter. So radius is given 0.01 meter. It is at the potential 30 volt. The potential of the spherical cell is given 30 volt. And it is asking you to find out what will be the electrostatic energy of the cell. So I think if you know the formula, it's easy to find out. It's easy to guess what will be the answer for this problem. So for the spherical cell, if you recall the electrostatic energy, it is q square by 8 pi epsilon naught A, right? And for potential, it is q by 4 pi epsilon naught A. So potential is given, so you can easily write out the electrostatic energy in terms of potential or in terms of the parameters that is given to you. So potential in R is given. Express the electrostatic energy in terms of this parameter. Then solve the problem to find out the answer. So W is Q square by 8 pi epsilon naught A. So you can square it so that you can compare it to the potential. In the sets, you need to multiply the constant so that the potential energy remains unchanged. So the first, this is nothing but the potential square 2 pi epsilon naught A. All the values you know, 1 pi 4 pi epsilon naught is 9 into 10 to the 9. The radius is given 0.01 millimeter per meter and V is given 30 volt. So work done will be, the electrostatic energy will be 30 square into 9 into 9 is 0.01. So this will give 5 into 10 to the minus 10 joules. So answer will be option C. Okay. This is a direct formula based problem. Next, um, in the next case, it's also quite similar to question number 2. So I will let you solve this problem and let me know the answer. Okay. First, let me read out the question. So there is the electrostatic energy in terms of 1 by 4 pi epsilon joule of a uniformly charged spherical cell of total charge 5 coulomb and radius 4 meter is. So you need to find out what is the electrostatic energy of a spherical, uniformly charged spherical cell, which is a total charge 5 coulomb and radius is given, it is 4 meter. So what will be W for this case in terms of units? 1 by 4 pi epsilon joule. 4 option is given. A is 2.675, B is 3.125, C is 4.425, and D is 5.895. Okay. Good that you are also solving the problems. So, question is easy. You know the formula. It is q square by 8 pi epsilon naught A. You know what is the and q and r is given. So you can express in terms of q and a. This is q square by 2a. Yes, so you both are correct. Answer will be option C. Okay. So sorry, option B. So 1 by 4 by epsilon naught is 9 into 21 9. Q square is it's given 25 and 2 into 4. So this will give. Okay, so we need to express in terms of 1 by 4 by epsilon, so you don't need to put 9 into 10 to the 9. So this will give 3.125 joule by 4 pi epsilon. Answer will be option B. Okay, so let's move to our next problem. So I will solve the problem because it will take some time to solve it. Go through the problems, go through the steps I am doing. If you have any doubt, let me know. Okay. So the problem is there is two long hollow coaxial conducting cylinder of radii R1 and R2. These are placed in vacuum. The inner cylinder carries a charge plus lambda per unit length, and the outer cylinder has charge minus lambda per unit length. The electrostatic energy per unit length for this system is. So we have a hollow cylinder which have surface charge distribution plus lambda and minus lambda. Inner one is radius R1, the outer one is radius R2, and inner one carries charge plus lambda, outer one carries charge minus lambda. So to find the electrostatic energy, you can follow any of the formulation that has been given in the lecture. So you can follow the rho v dv or whatever you are finding it convenient, you can follow it. So for this, if you use, if you know the electric field, then you can just use the formula epsilon by 2 square dv to find out the energy of the system. So W for this case is epsilon by 2 E square dV. So to find out the electric field, you can see it's a symmetric charge distribution. We can use Gauss law to enclosed by epsilon. So when R is less than R1, what will be the charge enclosed? It is 0, right? So charge is distributed at the surface. So that means electric field is 0. For radius, for a region between R1 to R2, Q enclosed will be the total charge at the at the inner cylinder. So this will be lambda dl. It's sorry. So Gaussian surface will be like a cylindrical one. So if you take a length, so this will be like this. Let's say this length is L. So total charge will be lambda L. And ds will be surface area will be 2 pi RL lambda L by epsilon. So electric field inside will be lambda by 2 pi epsilon naught R cap. And for R greater than R2, what will be the total charge? It will be 0, right? Because in outer surface there is a charge distribution of minus lambda. And it's a uniform charge distribution. So total charge will be lambda L minus lambda L. It's 0. So electric field outside is 0. So we have electric field now is 0 for R less than R1, lambda by 2 pi epsilon naught R, R cube for R between R1 to R2. Third point means I think you are referring to this one, right? So for R greater than R2, so when you are taking the Gaussian surface, sorry, let me take a different. So when you are taking a surface outside, So it's the charge Q enclosed. It will be inner one, which is lambda L. Outer one, outer it is minus lambda. So it is minus lambda L. That is why the Q enclosed is 0 for this case. It's a uniform charge distribution. So Q enclosed is nothing but lambda dl. Okay. And inner side we have plus lambda, outer side we have minus lambda. Length is same. Length of the cylinder is L for both the case. So that is why the charge enclosed is 0. Is it okay, Srishti? Is the doubt clear now? Okay. So mm, in outer we have 0 charges. So these steps do it as much as possible so that you don't get confused. Also, you will be more comfortable while doing other problems also. So don't neglect this kind of problems because uh, uh, if you solve many problems, it will you will be more comfortable and your uh, problem solving speed will also increase. Okay. So for all space, now we have only the reason between the cylinder. So from R1 to R2. E square is, E is only non-zero between R1 to R2. So that's why we are taking the integration between R1 to R2. Lambda square dV will be for cylindrical surface, this will be 2 pi R L dr. So lambda square epsilon naught to 2 pi. Okay, so 2 pi will cancel. So let us solve the inside first. Lambda square 4 pi epsilon square r square 2 pi r in dr. And r will cancel also. So we have epsilon by 4 lambda square L dr. dr by r. R1 to. Okay, so 1 pi will also be here. So this is lambda square. I think epsilon will also cancel, right? One epsilon will cancel. So you have lambda square 4 pi epsilon naught L ln R. So this is ln R. So ln R2 by R1. So this is the total electrostatic energy. The question was asking about the electrostatic energy per unit length. So that means the L won't be here. This will go to this side. So you have lambda square by 4 pi epsilon naught ln R2 by R1. Answer will be option B. Okay. Just calculate the electric field whenever you are given a charge distribution. If it is a discrete, so you say you have to sum it off over all the charges. You have to bring one charge one by one, then see how the energy is increasing. But for continuous charge distribution, you can find out the electric field in different region, then use the integration formula to find out the what will be the electrostatic energy. Okay. So I hope that is clear. Now we'll see the next problem. Next problem is quite easy. So I will let you to find out the answer. So question is a conducting sphere of radius r has charge q on its surface, and if the charge is doubled and the radius is half, then what will be the electrostatic energy associated with the electric field? How it will be, how it will change when you increase the charge by doubling it, or when you reduce the radius by making it half of its initial value. Let me know the answer. Option D. Yes, you are correct. So it's a conducting sphere, so it is similar to and the charge is residing at the surface. So that means you can use the for electrostatic energy for the spherical cell, which is nothing but q square by 8 pi epsilon naught a. You can see the electrostatic energy is directly proportional to q square and inversely proportional to a. Now you just need to take the ratio square and this a1 by a2. So given the radius is half of its initial value, so this will give 2, and the charge is also doubled. So this will be 2 square. So the electrostatic energy, it will increase by 8 times of its initial value. And, okay, good. Now we'll see the next problem. The next case, we have a point dipole moment P, which is P z2. It is located at the origin. Now it is asking you to find out what is the work done in moving a charge from point 0 b 0 to 0 0 b. This is also easy. You just need to remember what is the formula associated with the point dipole. So calculate it and let me know the answer. So you need to recall what is the potential associated with the point dipole, then you can use the potential to find out what will be the total work done in moving a charge uh, from a point 0b0 to 0, 0b. Anyone? Option B. Okay. Okay, let me solve it. So if you recall the potential associated with a point dipole, you can write it as 1 by 4 pi epsilon naught P dot R cube by R square. So it is for the dipole, we can, this is the this is the dipole potential, P dot R K by R square. So you are given P, also R is also given. So let us see whether which of the option is correct. So work done is Q, potential at the final point 0b0, sorry 0, 0b, and potential at the initial point 0b0. So potential is, the formula is given. So let me write 1 by 4 pi epsilon naught is beta. So P is given, P zk, okay. And the point R is also at the z axis, which is B. So R is also, this is also zk, and this is B square, right? And for the second case, this will be P zk, and the observation point is at y direction. So R cap will be yk. This. So this is 0. So we will get beta qp by b square. So qp by 4 pi epsilon naught b square. Okay. Answer, I think option D. 4 pi epsilon P square. Yes. Was this clear? Okay. So let us move to our next problem. So this is about how you can calculate the work done for a when you have a discrete charge distribution. I think all of you know the steps. You need to bring the charge one by one. Then you can just add the electrostatic potential energy, and you will see. And when you add it up, you will find the total energy of total energy to assemble this charge distribution. Okay. So let me do it. So you have four charges. PQ or at the origin, minus 2Q here, Q here, minus Q here, and Q here. Okay. So now let us take Q1 is PQ, Q2 is minus 2Q, and Q3 is minus Q, Q4 is Q. So if you start with Q1, when you bring the charge 3Q, so there was no electrostatic field which was already present in the system. So that is why when you bring 3Q, there will be no work done. So for the amount of work done that needs to be done is 0. For Q2, as Q1 is already present, so this will create an electrostatic field. So that is why we'll see there will be a work done when you bring the charge minus 2Q from infinity to the distance here. Okay. So work done is nothing but summation of Qi Qj by 4 pi epsilon Ri at J. So here it will be Q1 Q2 4 pi epsilon naught R12. So distance between 2Q and minus 2Q, this is the distance, which is nothing but root 2a. So this will be minus 6Q square 4 pi epsilon naught root 2a. Now we'll bring charge 3 when we have charge Q2 and Q1. This is not done now. So for Q3, we need to do work against Q3 as well as Q1. So this will be Q1, Q3, 4 pi epsilon naught R13 plus Q3, Q2, 4 pi epsilon naught R23, R32. So distance between Q1 and Q3 is A, right? Sorry, 2A. So this will give 3Q minus Q, it will give minus 3Q square, 4 pi epsilon naught, 2A plus Q3, Q2. The distance is this one, which is root 2A. So that is why you will get minus, 2Q square, 4 pi epsilon naught, root 2A. So this is Q square, 4 pi epsilon naught, 2 root 2 minus 3 by 2. Okay, now for Q4, you need to do the work against Q1, R14 plus as well as Q2, R24 plus Q3, total epsilon R3. So Q1, Q4, these are separated by distance, this way. So this will give, this is 3A and this is A. So I think it will give root 10A. So 3 Q square 4 pi epsilon naught root 10A plus Q2 Q square. Q2, sorry, Q2 Q4, this distance is A. So it will give minus 2Q square 4 pi epsilon naught. What is the distance? Sorry, distance is 2A. This is at A, this is 3, so 2A. And Q3, Q4, this is Q3, Q4, this is at a distance root 2A. So it will be minus Q square 4 pi epsilon naught root 2A. So we have now Q square 4 pi epsilon naught. And it will be 3 root 10 minus 5 root 2 minus 10 by 10. So total work done will be the summation of all the work. And you just need to add this one, three, what else? And this one, and this. So if you add it up, this will give Q square 4 pi epsilon naught 3 root 10 minus 25 root 2 plus 1 by 10. Okay. So this is the process, the steps that you need to follow when you have a discrete charge distribution. So is the problem clear? I will move to our next question. The next question is to find out the electrostatic energy stored in a spherical cell. And this cell is inner radius A and outer radius B. And it also has a charge distribution. Volume charge distribution rho is K of square. So we have a cavity here. Or inner radius is A, outer radius is B. And we fill the space with the volume charge rho is kr square. Work done, if you recall, it is epsilon by 2 v square dv in all space. And the charge distribution, it's symmetric one. So you can use the Gauss law to find out the electric field. Inside for R less than A, there is no charge. So for this Gaussian surface, there is no charge. So that is why we'll get is 0. And for in between A, R, B, you can use P dot D is enclosed by epsilon. So for this spherical cell, you need to take the spherical Gaussian surface. So it will give E 4 pi r square, and Q enclosed will be rho dV. So rho is K r square. dV is 4 pi r square you can take because theta and phi is in the whole integration. Theta you can in the maximum limit. So that is why you can take 4 pi r square. And for R, the for inside, we need to start from A to R. So 4 pi will cancel. The field is 1 by epsilon naught naught square K r to power 4 dr from A to R. So this is nothing but K r to power 5 minus A to power 5 epsilon naught naught square, and the direction is in the direction of the radial vector. So this is for the inside the cavity. Now, when you take a region outside the cavity for r greater than b, here you can take E 4 pi r square, and the charge is only enclosed inside the cavity, right, from A to B. So that is why the integration here is from, okay, so let me write it properly. 1 by epsilon naught from A to B, K whatever 4 dr. So this will give 3 by 5 epsilon naught d to the 5 minus a to the 5. So electric field we will get is there will be 4 pi K by 5 epsilon naught r square a to the 5 minus a to the 5. Okay. Now we know the electric field in different region, all the space. So now we can use I can see you have it out here. So why didn't you cancel r square on both sides? So you mean the r square here and the r square here? So this you can't cancel it because this r square it's related to the integration of dA. So when we take the integration of dA for the spherical surface, we get r square, right? But this r square is still inside the integration. So you can't take it out from the integration because uh, only you can only the constant you can take it out from the integration. Like k is a constant here, so that's why you can take it out. But r square you can see it's a variable here. There is an integration on dr. So that is why I haven't cancelled r square and r square here because it's not allowed. This r square, if you recall, mm, I can explain it. So for a spherical Gaussian surface, if we recall for the radial direction, uh, let me take a page. So the dA vector in radial direction, this is in the radial direction. This is r square sine theta d theta d phi, right? It's in the radial direction. So when we take the integration here, for this case, so when we consider a spherical surface here, uh, for this case, this r square is constant. You don't need to take the integration, and because here the variable are d theta and d phi. So you are looking at the surface, not the volume. So that is why r square is constant here, and this will give 4 pi r square. So in this way, we get for the left hand side, we got 4 pi r square. But in the right hand side, you have rho dV, right? And for that case also, here the radius it's not a constant because you are looking at the volume now, not at the surface. So that is why if you look it, so it is k r square sine theta d phi. So here the radius is also a variable, and sine theta d phi it will give a if you take the integration, if it will give 4 pi, and this will give 4 pi r to the 4 dr. So r square is still inside the integration. So that is why I haven't cancelled on both sides. Okay. So I hope this is clear now. So I haven't cancelled r square. Okay. So now you know the variables, sorry, the electric fields. So finding out the work done is now easy. It is epsilon by 2 E square dV integration over all space epsilon by 2. Inside the, so we have a cavity here, right? And the charge is distributed here. So from 0 to A, there is no electric field, so this will be 0. From A to B, there is a electric field, which is this one. So we'll use this for A to B. The electric field is K r to power 5 minus a to power 5 5 epsilon naught r square dv. You can write it as 4 pi r square dr. Okay. So here the r square which is inside the integration, this you can cancel it. And the other integration that we have is from B to R. Sorry, from B to all space, that is infinity. So in this region, the electric field is K b to power 5 minus a to power 5 5 epsilon naught r square 4 pi r square dr. R square will cancel. Okay. So it will be square, right? A square. So I think you can easily find out the integration, right? This is 4 pi, there is 5 epsilon naught, a to b, r to power 5 minus a to power 5 square dr plus 4 pi by 5 epsilon naught d to infinity bit word. Okay, so these are constant. Now you have dr. Um, I think there will be a square. Okay, so I did a mistake. So this is r square, right? So one r square will remain because it will be r to power 4. R square will remain 1 by r square from b to infinity. So just do the integration. I think you can easily find out. So you will get the answer is way right. I forgot one r square in the denominator. R square. 5 a square by 55 epsilon naught 5 a to the 4 minus 9 a to the 5 b to the 4 or b to the. Just check once whether you are getting the answer or not. Okay. This will give 1 by r and this will we have to simplify it. Okay, so now let us move to our next problem. So I will let you to find out the answer. So there are charges q, 2 plus q charges and 1 minus 2q charge. These are placed at the vertices of equilateral triangle ABC, which is side length A. Okay, the figure is not here. Let me make it. Okay, minus 2q. You need to find out the dipole moment of this configuration of charges irrespective of the choice of what is it. So there are four options given. Find out the dipole moment. Option D, 0. Check it once. You need to recall what is the formula we have used for finding out the dipole moment. For monopole, it's easy because I think you were talking about monopole. Monopole, it's nothing but the summation of all the charges. For discrete charges, it's the summation of all the discrete charges. So you can see it here, it is minus 2q, q, and q. So this monopole moment is 0. So there will be no contribution to the potential from monopole moment. But for this case, you need to find out the dipole moment. Recall the formula once. Okay, so if it is taking time, let me solve it. Okay, option D. Just let me write out the steps. Check whether you have any doubts in the steps. Okay. So if you recall the lecture, whenever the total charge of the system is zero, that is the monopole moment is zero. So for that case, the dipole moment, it doesn't depend on the origin that you are taking. So you can take the A point as the origin, or you can take B as the origin, or you can take C point as the origin. So whichever origin you can take, and you will get the same answer. So that is why we say whenever the monopole moment is zero, then you will get that the dipole moment is irrespective of, you will get the same answer irrespective of the origin you are taking. I think you are correct. The answer will be option C. Okay. So if you recall the dipole moment, it is r prime rho r prime dv, right, for the integration. But for the discrete charge distribution, we can write it as summation of r prime I charge qi, which is located at ri prime. For I, for this case, it is three charges, so I will run from 1 to 3. Okay. You can take A as the origin point, 0, 0. You can start, this is 0, 0, or this will be. Then you can name the coordinates according to A. Or you can take A as some random coordinate. Let's say A is xy. We don't know the coordinate here. Let's say A is xy. So if A is x, A will be A plus x, y, and C will be uh, x plus A by 2, y plus root 3 A by 2. Now we know the coordinate. So this is nothing but R A prime, R B prime, R C prime. So we know the coordinates. So let us calculate what will be the dipole moment. So P will be Q R A prime, which is x I k plus y j k plus Q R B, which is A plus x I k plus y j k. The third charge is minus 2q, which is at the point RC. So this is minus 2q. RC is x plus u by 2 ik plus y plus root u by 2 jk. So we have q, if you add this will be 2x plus a ik plus 2qy jk minus 2q. This will be q 2x plus a ik. So I've just simplified and I've cancelled 2 here with the 2 and minus 2 to y plus with 3. From this you can see this one will cancel with this, and okay, the whole will cancel, And the 2qy here will cancel with 1 2qy here is jk. So we have now minus root 3 raised to jk. So answer will be option C. Okay. So is this clear? This problem? Feel free to ask me the doubts if you are having any small query in the steps. Okay. So let me move to next problem. For the 10th question, it's related to question number 9. So you have find out what is the uh, what is the dipole moment of the charges when you place it on the equilateral triangle. Now we need to find out what is the electrostatic potential energy for this system. So when you have a charge plus QU minus the QU. So this is easy, right? Because the system is not that complicated. So you can use the normal summation rule to find out the total potential energy. So Q1 is 2, Q2 is 2B, Q3 is 2C. So the potential energy is W12 plus W23 plus W31. W12 is, these are separated by distance A, so this will be Q squared by A. 2, 3, so okay, all the distance are A. So Q3 will be minus 2K squared by A, and C1 will also give 2K squared by A. So this will be K squared K is 1 by 4 pi epsilon naught. Okay, so let us move to our next problem. This is related to the continuous charge distribution. So you have a circular ring of radius r. It has a linear charge density. Lambda theta is. Let me draw it first. We have a ring and it has a linear charge density. This is by lambda theta is lambda 0 sine theta by 2. So theta will be, so this is the angle theta, right? So theta will be from 0 to 2 pi. So for this case, you need to find out what will be the monopole moment and what will be the dipole moment for this charge distribution. Okay. So for continuous charge distribution, we need to take the integration and monopole moment, if you recall, it is rho dV. If you have a volume charge, it is rho dV, but for a line charge, Q will be lambda dl, right? Lambda theta dr prime theta. Lambda is given is lambda 0 and theta by 2 and dr. So small length element. This will be the small length element which will be r d theta, right? For a small angle d theta, here this length is r d theta. Theta will be from 0 to 2 pi. Lambda 0 duration 0 to 2 pi sin theta by 2 d theta. So sin theta by 2, this will be 2 minus cos theta by 2, 0 to 2 pi. So this will give a value of 2. So the monopole moment for this case is 4 lambda 0 r. Okay, for the line charge density. For dipole moment, is r prime, or for line charge density is r prime lambda theta dr. So first you need to see what is the location of this line charge density from the origin. That is what we mean by r prime, right? R prime is the distance from the origin to the charge element. So R prime is, I think you can easily guess. So this is R prime, right? This is the position where the length element is there. So this you can write it as in terms of xy coordinate, R prime theta. This will be R cos theta theta plus R sin theta jk, right? So now we know the R prime. So dipole moment is R cos theta theta plus R sin theta jk. Lambda theta is lambda 0, sin theta by 2. Dr is R d theta. So we'll get lambda 0 R square duration cos theta sin theta by 2 d theta I cap plus j cap sin theta by 2 d theta. So we have two components. One is in the x direction, one is the y direction. So px is lambda 0 r square 0 to 2 pi cos theta sin theta by 2 d theta. So you can express cos theta in terms of sin theta by 2. This you already know. This is cos theta is 1 minus 2 sin square theta by 2 sin theta by 2 d theta. So it will give lambda 0 r square 0 to 2 pi sin theta by 2 d theta minus 2 0 to 2 pi sin square sin cube theta by 2 d theta. This will give lambda 0 r square. First integration, check the integration values whether you are getting or not. This will give 4 and this will give 16 by 3. So you will get minus 4 by 3 lambda 0 r square. This is for px. For py, we have lambda 0 r square 0 to 2 pi sin theta by 2 d theta. Similarly, you can express sin theta in terms of sin theta by 2. So this is 2, 0 to 2 pi sin theta by 2 cos theta by 2. And again, we have a sin theta. Okay, lambda 0 r square 0 to 2 pi sin square theta by 2 cos theta by 2 d theta. So it is in terms of x dx, and this will give sin 2 theta by 2. But if you see the limits, it's in the range 0 to 2 pi. So sin 0 will be 0 and sin 2 pi will be 0. So just check. Uh, I think you will get the value of 0 here. So dipole moment is minus 4 by 3 lambda 0 r square. Okay. Okay. So is this problem clear to you? Do you have any doubts? If not, let us move to our next problem. It's quite easy. So the question is asking, there are three equal charges Q are successively brought from infinity, and each is placed at one of the three vertices of equilateral triangle. Assuming the rest of the universe as a whole to be neutral, the energy E0 of the electrostatic field will increase successively to E0 plus delta 1 when you bring charge Q1, and when you bring charge Q2, it will increase to E0 plus delta 1 plus delta 2, and when you bring charge Q3, it will increase to E0 plus delta 1 plus delta 2 plus delta 3. So you need to find out what is the ratio of delta 1, delta 2, and delta 3. Calculate it and let me know the answer. Because this is a discrete charge distribution, you just you need to use the summation rule. Just use that and let me know which of these following is the correct answer to this problem. Calculate one by one. What will be delta one when you bring a charge q from infinity to a distance, let's say a. Then calculate what will be the delta one plus delta two when you bring charge another charge q from infinity to a distance, some distance. Then I think you can. Okay, so it's already given. These are placed at the vertices of equilateral triangle. Distance are same. Answer is quite easy. Yes, you're correct. And option D is the correct one because when you bring charge q from infinity to the distance a, let's say this is the q charge you are bringing, so there will be no work done that is required, right? So that is why answer will be sorry. The work done for bringing the charge q is zero. Now, when you bring the next charge, you need to do the work against the charge that is already present, and the distance between them is q. So this will be q square beta by a. And for delta 3, it will be work against both the charges. So this will give 2 beta q square by a. So delta 1, delta 2, delta 3 will be 0, 1 is to 2. Option D. Okay. Next problem. There are two charges, minus q and plus q. These are placed at, you can see in the figure, it is at minus is 0 and plus q is at a. Okay. And shown in the figure, right? And now we are changing the origin from, let's say the origin was first here, but now we are moving the origin to xy. What will be the magnitude of the dipole moment given the configuration with respect to the new origin? What will be the answer? Option B. Yes, you are correct. But I think looking at the time you took, I think you have calculated the dipole moment with respect to xy, right? So you have find out the coordinate of q with respect to xy minus q with respect to xy. Then you just sum it up to find out the dipole moment. You can follow that step also. But if you recall the concept, whenever the total charge is zero, whenever the system is total charge is zero, then in that case, it doesn't depend on the. Yes, yeah, yes, your answer is correct. But I'm telling you one of the shortest method. Like you can see the total charge here is zero, right? So it doesn't depend the origin you are taking. In XY, you will get the same answer if you take this point as a origin, you will get also the same answer. So the best way to do it is if you do it from with respect to this origin 000 because you know the coordinates, right? So this is ai cap, this will be minus ai cap, right? And dipole moment is nothing but summation of ri prime uh, qi ri prime for I 1 to 2. For q charge, this is q a I cap, and for minus q, it will be again minus q minus a. So this will be plus qa I cap. So that's why the answer will be 2qa I cap. So you can see how easily you got the answer, right? But if you follow the, it's not a wrong method, wrong process that you took XY also. That also give the same answer. Okay. But better to keep the concept in mind because it will be helpful for you to find out the answer in within 1 second. Okay. So that is why I've used the concept that we've seen that whenever you have the total charge is zero, then you can take any origin you want. You can take the origin here also. Like, no, don't take here, take it here. Okay. Or I think here also it will give the same answer. If you take this one as a origin, like this is 000. So minus q will be at my with respect to. Okay, I think I may be confusing you. So let me draw it. So what I mean is this is at minus q. This is minus a 0. So you can take this one is also a origin. So that is you are making a to a 0 to 0 0. That is we are subtracting minus 8. So you need to add here also. This will be minus 2a, right? With respect to plus q, this is at minus 2a 0. And you can see it here. The dipole moment will be 2aq, ik, right? Or you can start it from here. You can put it at the origin. You can find out the dipole moment is q to qa. It's up to you to find the steps that you want to follow, but it is one of the shortest method. Okay. Okay. So let us move to our next one. So for this case, the total charge is not zero, so you can't. So the dipole moment does depend on the origin. So be careful while writing the r prime vector. So for this problem, there are two charges minus q and for plus 4q. So these are at a distance d along the z direction. And the question asks to find out what is the monopole moment, what is the dipole moment, and what will be the electric potential in spherical coordinate for a distance r much greater than d by taking only the monopole and dipole contribution. So what will be the monopole moment here? Monopole moment is nothing but the summation of total charges. So this will give monopole moment will be PQ, right? Yes, you are correct. So summation of total charges. Whenever you have a discrete charges, just take the summation to find out the monopole moment. Okay. And dipole moment, for dipole moment, you need to find out R prime. So this is summation of Ri prime vector and Cy for I 1 to 2. So we can see Q1 is at origin 0, 0, 0, and Q2 is at 0, 0, Z, D. So that means this will give, because R1 is 0, R2, this is 0, this will give 4Q, D, ZK or KK. So this is the dipole moment. Now we want to find out the electric potential. So potential, if you recall, it is for monopole dipole, you can take this is monopole contribution, then dipole contribution. And because the monopole moment is 3Q, let me write the formula first. This is 1 by 4 pi epsilon naught, 1 by R, or I think here it is given curly R, 1 by R, summation of Qi plus 1 by R square, summation of Qi Zk plus, sorry, Zk dot Rk, it will give cos theta. So Ri and cos theta I flow. So 1 by 4 pi epsilon naught. This is 3Q by R is 4 2D cos theta by R square. This is due to the monopole contribution and this is due to the dipole contribution. Okay. So next we have a continuous charge distribution. So there is a sphere of radius r centered at the origin. It is a charge density rho r theta is kr by r squared r minus 2r sin theta. Here k is the constant, r theta the usual spherical coordinate. Find the approximate potential for points on the z-axis far from the sphere. So to find out the potential, we need to check the monopole term, potential due to the monopole, potential due to the dipole, and potential due to the quadrupole or any other higher order term. Okay. For monopole, or in the integration notation, we have 1 by 4 pi epsilon naught, 1 by r rho r prime dv prime plus 1 by r square r prime cos alpha rho r prime dv prime and the higher order term. So let us check one by one. Monopole moment is rho r prime dv prime. Rho is given. It is k r by r square r minus 2 sin theta. You can see rho r is a function of r as well as theta. So it's better to take dv as r square sin theta d theta. D phi will give 2 pi and dr. This r square will cancel. So you have 2 pi r integration of r minus 2r. Sorry, these are r prime, right? These are all r prime, the location of charges. R minus r prime dr prime from 0 to r and sin square theta d theta from 0 to pi. If we look at this integration, this will give r square, right? R square minus r square. So that is why this will give, then total integration will be 0. So there is no contribution to the due to the monopole moment. Now we'll look at the dipole one. For dipole moment, we have r prime cos theta rho r prime dv is r prime square and theta beta 35 dr prime. So we kr 0 to r prime r minus 2r prime dr prime 0 to pi sin square theta d theta and 2 pi. I think cos theta will be there, right? This one, cos theta. And this is 0. Integration of 0 to 2 pi sin square theta cos theta d theta within the limit 0 to pi. This is 0. So that is why quadrupole movement is also, sorry, dipole movement is also 0 here. So that means the next dominant term will be the quadrupole one. For quadrupole moment, we have integration of r square p by 2 cos square theta minus half rho r prime dv prime. So you will get kr by 2 0 to r prime square r minus 2r prime dr prime 0 to pi p cos square theta minus 1 sin square theta d theta and 2 pi. For d5, d5 will get this. So for the first one, 0 to r prime square, r minus 2r dr prime. For this one, you will get r to power 4 by 6. Okay. For the second one, for theta, you have p cos square theta minus 1 sin square theta d theta. So you need to express in terms of either sine or cos to simplify the integration. So let's write cos in terms of sine. So this will be, whole term will be 2 minus 3 sin square theta sin square theta d theta. It will take some time to find out the answer because it is 2 and 3 terms that you need to find out the integration carefully. 3 sin 4 theta d theta. Your next step is to express sin square theta in terms of 1 minus cos 2 theta. And this will be 1 minus cos 2 theta square. Just do it. Okay, I think it's you can easily find out the integration. If not, let me know in the next live session. For now, let me just write out the answer. You will get 3 pi by 2. So I think the total we'll get is minus pi by 8. So quadruple moment is 3 r by 2 r4 by 6 minus pi by 8 and 2 pi. We have k I square or 5 by 48. So now you can easily write the potential is the dominant term for the potential will be quadruple one, which is 1 by 4 pi epsilon naught k pi square whatever 5 divided by 48. The distance is zk. Okay. So do you have any doubt till now? Next question is easy. Yeah, for this, it's a discrete charge distribution, and for this discrete charge distribution, you need to find out what is the potential valid at a point far from the origin. So, can you let me know what will be the monopole moment? Whether the potential will have any monopole contribution or not? What will be the monopole moment? Yes, monopole moment is zero. So that means there will be no contribution of monopole moment. Now let us see the dipole moment. Calculate it and let me know what will be the dipole moment. You can see it here, the total charge is zero. So that means whatever origin you take, it doesn't, dipole moment doesn't depend the choice of origin. So just use the origin according to your own convenience and find out the answer. You can take this also as origin if you want. Okay, let me write out the answer. So if you take this as a origin, the 3q will be at 3q will take it. Minus for this one, we have minus 2q a I cube. For this one, we have plus 3q a I cube. And for this one, we have minus q a t cube. So it will give 2qa t cube. So the dipole moment is non-zero. So when you find out the potential, the dominant term will be the dipole term. So that is why you can approximate the potential as potential of dipole, which is 1 by 4 pi epsilon naught r cube p by r square. And it is in the, this will be 1 by 4 pi epsilon naught r cube z cube by r square to q. Okay. R cube and z cube, you can write it as cos theta. Okay, so let us solve our final problem. So this will be our last problem that we will solve. So it's given there are two charge distribution, which is charge density rho as q delta x minus x0 minus delta x plus x0. For this configuration, find out the electric field at 2x0. So let me tell you the answer for this. So for this one, you can see the observation point 2x0. It's quite close to the point where the charges are located. So from this expression, you can see one charge minus q is at minus x0 and one charge q is at x0. So, and the point is the point where we want to calculate the electric field is at 2x0, which is quite close to the point where the charges are located. So don't use multiple expansion here. When multiple use multiple expansion whenever it's not given, the point is closer to the. If it is not given, the point is closer to the charge, the point where charges are located. If it is not given, then you can always take multiple expansion. But if it is given, the point is given, it is, and you can see the point is closer to the charge distribution. Then what you need, don't use multiple expansion, just use the normal summation rule to find out the electric field. So you know what is the electric field produced by minus q at the point here and plus q at point here, right? And add it up to find out the total answer. And do it. Now, let me just tell you the answer. And option A will be the answer. Just check it once, okay? So we'll stop for now. Do you have any doubt in any of the problem? Yeah, I think if you have, if you don't have any doubt, let us end our session here. Thank you for joining the session. I think the problems that I've solved will be helpful for you to solve the assignment problem of week 6. And let us meet on next Friday, same time from 6 to 8, to solve few more problems related to capacitor, dielectric, and contents that is related to week 7. So thank you for joining the session. Let us meet on next Friday. So goodbye everyone.